Have you ever wondered, when you're moving on a motorcycle or a bike with high velocity, there is a lot of wind moving around you and your nose, yet you are likely to experience difficulty in breathing compared to when you're at rest. Or in other case, consider taking two balloons slightly placed apart from each other. Now try blowing air between the two balloons with the help of a hairdryer. One would most likely expect that two balloons to move apart from each other, but that wouldn't be the case. Instead, they would come closer to each other and stick together. But why is it so? For that, we need to look at the Bernoulli's principle. Given by Daniel Bernoulli, a Swiss scientist in 1738, Bernoulli's principle is applicable only for dynamic fluid, meaning a fluid that is in a steady flow. Bernoulli's principle is only applicable to ideal fluids. An ideal fluid is a fluid that is incompressible, non-viscous, and without surface tension. Bernoulli's principle is generally governed by law of conservation of energy by definition. We previously discussed that Bernoulli's principle is applicable only to fluids in steady flow. But what exactly is steady flow? Steady flow is also called streamlined flow. In a streamlined flow, particle at every point will not have the same velocity, but every particle passing through a particular point will have the same velocity. For better understanding, let's consider pipe B. Now consider a point A where the velocity of fluid particle is v1. Consider another point B where velocity of fluid particle is v2 and v1 is not equal to v2. But in a streamlined flow, when the particle at B arrives at A, its velocity must change to v1 and every particle that arrives at point A must have the same velocity v1. But velocity at two different points like A and B may not necessarily be the same. Such type of fluid flow is called streamlined or steady flow. Now let's understand the Bernoulli principle by analyzing the Bernoulli equation. According to Bernoulli principle, when an ideal fluid is flowing steadily, then at every point the sum of pressure, kinetic energy per unit volume, potential energy per unit volume remains constant. Hence, by deduction, Bernoulli equation would be as follows. Here, pressure is given by P, G gives the acceleration due to gravity, V gives the velocity of fluid at a particular point, H gives the height of the fluid from the reference line, and rho gives the density of the fluid. Here, in order to find kinetic energy per unit volume, let's divide volume on both sides. On the right hand side, we have mass upon volume, which gives density of the fluid rho. Hence, kinetic energy per unit volume would be half rho v square. Similarly, by dividing volume on both sides, we get potential energy per unit volume on the left hand side and rho gh on the right hand side, where rho again is the density of the fluid. The Bernoulli equation can also be verified dimensionally by following the principle of homogeneity, where every term separated by a plus or minus sign has the same dimension. Now let's consider 2 points from a pipe with flowing water. At point 1, the sum of pressure, kinetic energy per unit volume, potential energy per unit volume must be same as that in point 2. This would in turn verify the validity of Bernoulli principle. There are many applications of Bernoulli's principle that may go unnoticed in daily life, but its major applications are in the field of aerodynamics and aviation and in the construction of venturimeter. In order to understand the applications of Bernoulli principle and the initially proposed questions, we need to understand the relation between velocity of fluid flow, area of cross-section of the pipe, pressure, and height of the fluid flow from the reference line. Such relations can be deduced from the Bernoulli equation. Now let's derive the relation between pressure at a particular point and velocity at that particular point. We previously equated the sum of pressure, kinetic energy per unit volume and potential energy per unit volume of two different points. But this time we will be equating the net sum of two different points for a fluid flowing in a pipe with non-uniform cross-section as shown. Now consider 2 points 1 and 2, where at point 1 area of cross-section is A1, velocity of fluid flow is V1 and pressure is P1, and at point 2 area of cross-section is A2, velocity of fluid flow is V2 and pressure is P2. In this case, the height of fluid flow from any particular reference lines is same since the fluid is flowing in a straight line. Therefore, H1 at point 1 is equal to H2 at point 2 between any 2 points. Since height of fluid flow is same for all the points, hence potential energy per unit volume also remains constant throughout the pipe. Now, by moving the potential energy term to the right hand side of the equation, we get P plus half rho V square is equal to constant. We can now derive the relation between pressure and velocity of fluid flow from the obtained equation. From the obtained equation, it is evident that if pressure increases, the velocity of fluid flow must decrease, since the net sum must be constant. For better understanding, consider the equation x plus y is equal to 4, where 4 is a constant. If x is 1, then y must be equal to 3, and if x is equal to 2, then y must be equal to 2. Similarly, if x is 3, then y must be 1, and if x is 4, then y must be 0. As you can see, as x value increases, y value decreases, and vice versa. Hence, from the equation, if the value of pressure increases, then the value of velocity of fluid must decrease, and vice versa. Or in other words, pressure is inversely proportional to velocity of the fluid. From the figure, it is evident that area of cross-section at point 1 is less than that of area of cross-section at point 2. As a result, velocity of fluid at point 1 must be greater than the velocity of fluid at point 2 because of equation of continuity, which says that velocity of fluid flow must be inversely proportional to that of area of cross-section. Therefore, pressure at point 2 must be greater than pressure at point 1 because of the result we derived previously. From the obtained results, it is also clear that pressure at a point is directly proportional to that of area of cross-section. So the final results are: pressure is inversely proportional to velocity of fluid, and velocity of fluid is inversely proportional to area of cross-section, which is nothing but equation of continuity. And finally, pressure is directly proportional to area of cross-section. We have now arrived at the relation between pressure and velocity of the fluid flow. Now let's try to answer the initially proposed question about why two balloons stick together when air is blown between them. In a region between the balloons, say region A, velocity of air is high, hence pressure is low. And in a region other than region A, say it region B, the velocity of air is low, hence pressure is high. As a result, the balloons move from the region of high pressure to the region of low pressure and finally stick together. Conclusion: balloons will move towards the fast moving wind since pressure is low there. We will now try to derive the relation between height of fluid flow from the reference line and pressure of the fluid. Consider 2 points 1 and 2. Now the height of fluid flow at point 1 from the reference line is H1 and the height of fluid flow from point 2 from the reference line is H2. Pressure at point 1 is P1 and at point 2 is P2. In this case, the pipe has a uniform cross-section throughout the length, hence area of cross-section remains constant, and therefore velocity of fluid flow also remains constant throughout. Hence, kinetic energy per unit volume remains constant, since it depends on velocity of fluid flow. Now by moving the kinetic energy per unit volume term to the right hand side, we get P plus rho gh is equal to constant. From the equation, it is clear that if pressure increases, the potential energy per unit volume must decrease. For potential energy per unit volume to decrease, the height of fluid flow must decrease, since potential energy per unit volume depends on height of the fluid flow. Therefore, it can be concluded that pressure is inversely proportional to height of the fluid flow from the reference line.